So we're going to look at question 15A from the textbook, section 1.6. Now, I gave you 15 and 16. Might have also given you 14, but we're just going to do this one question together. And what we're going to do is the question asks us to find a basis for and the dimension of each of the following subspaces. And instead of answering that question, we're first going to prove that this subspace or this subset that's defined by W is in fact a subspace. Then once we've proven it's a subspace, we're going to create a set such that W is a subset of the set of the span of S. Then we're going to show that that set S is a basis for W. And finally, we're going to calculate the dimension of W. So first things first, we want to show W is a subspace. To do this, what we're going to do is we're going to let the X and Y be in W and C be in set of real numbers. Now, why did I pick real numbers? Because my field is the set of real numbers. Then I'm going to redefine what X and Y are. X equals the set A1, B1, C1, D1, such that A1 plus 2B1 equals C1 minus 3D1 equals 0. And Y equals A2, B2, C2, D2, such that A2 plus 2B2 equals C2 minus 3D2 equals 0. Consider Cx plus y. Cx plus y equals C times A1, B1, C1, D1 plus A2, B2, C2, D2, which equals CA1 plus A2, CB1 plus B2, CC1 plus C2, CD1 plus D2. And now we want to verify that it satisfies this condition. So note that C A1 plus A2 plus 2 C B1 plus B2 equals C A1 plus 2 C B1 plus A2 plus 2 B2, which equals C A1 plus 2 B1 plus A2 plus 2 B2, which equals C times 0 plus 0, which equals 0. Likewise, C1 plus C2 plus 2, or sorry, minus 3 C D1 plus D2 equals C1 plus, sorry, I wasn't expanding it correctly, minus 3c d1 plus c2 minus 3 d2, which equals c bracket c1 minus 3 d1 plus c2 minus 3 d2, which equals c times 0 plus 0, which equals 0. Therefore, x cx plus y is in W. For all x, y in W and c in F. Thus, W is a subspace. So I've shown that W is a subspace. Okay, so that's the first part of the problem that we're going to do. We're going to show that W is a subspace. The next thing that we're going to do is we are going to create a set S such that S is a basis for W. Now, to create this set S, I typically follow 3 steps. First, let X be in W and create S such that W is a subspace of span F. 2, show that span S is a subset W. 3, show S is linearly independent. If not, remove redundant vectors until S is linearly independent. Meaning, I could have made a set S that has too many vectors, but it's a spanning set of W, meaning that the span of S is W, but it's not linearly independent. But because I know it's a spanning set, I can just remove a vector at a time that is redundant till I have a linearly independent set. Now, the way in which we construct S, this typically doesn't happen. Typically, we can ignore this step and just verify, yes, we are linearly independent. Now, how do we go about this? Let's create a basis for W equaling the set of A, B, C, D in M2 times 2 such that, and I'm just going to zoom in a little bit here and move over a bit such that A plus 2B equals C minus 3D equals 0. So let's zoom in a little bit and focus on this. So let X be in W. And I like to start with just a generic vector. Then X equals A, B, C, D, such that A plus 2B equals 0 and C minus 3D equals 0. And I here, whenever we have something equals something else equals a third thing equals 0, we're able to split that up into 2 expressions. The first one equals 0, the second one equals 0. Thus, and now here, it's going to be slightly different than what we've done, or you may have done previously. We've got to create a solution vector to a system of equations. So thus, the solution vector A, B, C, D is a solution to the system of equations A plus 2B equals 0 and C minus 3D equals 0. So my solution vectors to this system of equations aren't the vectors in W, but they can be used to create the vectors in W. You see how the solution vectors is just a vector A, B, C, D, and it represents the entries of the matrix A, B, C, D.